PDF ya. Oh, silakan dibuka.
Cek. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Dear distinguished speakers, lecturer, student, and all participants, welcome to the general lecture entitled Spintronics and Application, organized by the Department of Physics, Faculty of Mathematics and Natural Sciences, Universitas Gadjah Mada. I am Adistin Kajiananda, and I will be your moderator today. Thank you for joining us both offline and online via Zoom meeting. Ladies and gentlemen, we will now begin the event with the opening speech from Dr. Herlan Darmawan as a representative of Physics Department. Please welcome Dr. Herlan Darmawan to deliver his remarks.
Okay, good morning, everyone. Our honorable mention, Professor Nakamura from Mi University, right? And Dr. Mi-Jin JIN from IBS, South Korea. So if student want to see K-pop, you can contact her. But also, don't forget you have to study as well. So our warm welcome in our Faculty of Mathematics and Natural Science, especially in our Department Physics. And thank you very much for Professor Eddie. He is a lead in spintronic or magnetism, as I know, because I'm from geophysics. It's a little bit far away from the expertise. And actually I study volcano. So maybe relate with the Japanese colleague in your university. And we are very happy here because we have many students that really want to study about the magnetism or spintronics stuff in here. And I think if you want to strengthen our collaboration, we are very welcome. And we have, like you can see here, we have hundreds students in our physics department, including in a bachelor and graduate program, master and doctor. So we have a potential collaboration also with Korea. If you want to strengthen the research and exchange, we are very welcome here. And don't forget to enjoy food in Yogyakarta. We really like sweet stuff here. You can taste gudeg or something. And we have sweet stuff like bakpia. Yeah, you can enjoy the food as well. And the people are also very kind in Indonesia. We are always smiling. Yeah. So again, thank you very much. And I hope for the student, you should give your full concentration, right? Because we have a guest from far away from Japan and from Korea. And I hope the student can enjoy your guest lecture. Thank you very much.
Thank you, Dr. Herlan, for the opening speech. Now we will move to the main session. Today, we are honored to have two special, insightful, invited speakers. Our first speaker is Professor Dr. Kohji Nakamura from Mie University, Japan. Before we begin, allow me to briefly introduce Professor Nakamura profile. Professor Dr. Kohji Nakamura is currently a professor at the Graduate School of Engineering, Mie University, Japan. His research interests include spintronic device and first principle of electronic structure for new functional materials. He obtained his doctoral degree from Hokkaido University, 1995, as Assistant Professor, Department of Astrophysics, Northwestern University, United States of America, 1999, Assistant Professor, School of Engineering, Mie University, 2001, Associate Professor, Graduate School of Engineering, Mie University 2006, and Graduate School of Engineering, Mie University from 2018 until now. Professor Nakamura will present design of interfacial materials for magnetic tunnel junction. Ladies and gentlemen, please welcome Professor Dr. Kohji Nakamura. The presentation will be up to 45 minutes.
Middle. Okay. Nice to meet you. Thank you so much giving me opportunity to talk on my talk. First of all, thank you so much for the introduction, kind introduction. So today I want to be here. So my title is Design of Interfacial Materials for the Magnetic Tunnel Junctions. So this one, so my name is Kohji Nakamura from Mie University. Anyhow, it's take to probably many of the students or many of the people know about Japan. So they are almost 40 hours by flight. And then, so this work is fortunately already Dr. Josephine already presented in the last month in the online. Probably there is a duplication. Please patient. Okay. And then before starting on the my talk, I want to be introduce my university. Yes, compared to the UGM, this is a big university. Yes, but my university is very small, one order of magnitude smaller than the UGM. So for example, we have the undergrad student is about the 6,000. You have 60,000. Oh, big. And also my school is only the 60 division school, graduate school. Oh. Here, the Humanity Law and Economics, School of the Humanity Law and Economics, and School of Education, School of Medicine. I'm in the engineering, School of Engineering. So in engineering, we have a 60 course division. So one of them, so I'm in the electrical and electric engineering department. And then that's all my university introduction. And then, so I want to be show my lab. And then my lab name to Spintronics laboratory. This is, I'm sorry, this is Japanese. So indeed, this is present the member of our group. And then, so fortunately, I had a very nice student from the UGM and the former and present student from Indonesia. As I have the 1, 2, 3, 4, 5, 6, 7 students. And first of all, the Alvin, Professor Alvin, he is very smart, mathematics, very strong in mathematics he has. And then he get for the PhD at the 2022. And last year he stayed 1 year for my university. And next one is Dian-san. He from the UGM and he got for the 2023 for the PhD at my university, and he is now researcher, permanent researcher of the AIST. AIST is a National Institute of the Advanced Industrial Science and Technology in Japan. It's very nice institute. And then, so Josephine here, he also come from the UGM, and got for their 2025 for the PhD at my university. And she is now on the Tohoku University. She directly now working on MTJ project. And then so here is the Andy Chakti, he from the ITB, Bandung Institute of Technology. And then he got for the PhD 2026, just 2 months ago. And he is now in Korea, moved to Korea, and he working at the KAIST, Korean Advanced Institute of Science and Technology. Thank you so much for the report. And then also now presently I have a 3 PhD student, Andy Shamsul from the ITB. He is very smart for the machine learning. We starting for the machine learning project for the materials. And then Hidayati from the UGM. She is now working anomalous Nelson effect. And also the Fauzan, he is an exchange student. He is now to be bachelor student. He is very smart. And he can speak Japanese. And then he have many friends in Japanese with Japanese and traveling for any places in Japan without no difficulty for the language. Okay. So this is my activity in lab. So my major work is on the implementation of the first principle calculation. Probably you use for the first principle code from the like a VASP, quantum expression, or so many works. I'm also working on the programming. So my code is the FLPW method, and probably some of you know about for this equation. Look like a Schrödinger equation, but Kohji equation. So we try to solve for the X equation by computation. And then indeed, in this equation, we have so many approximation. So we have to take care of all of the things. So the black line show I already implemented for this kind of the option. And then so we categorize for the L matrix, P matrix, and J matrix, like this one. And also we studied for the machine learning for the material informatics. Mainly, I'm working on the implementation of the first principle code. My student working on this one, because this one is written by Fortran. Do you know the Fortran? Okay, good. And this machine learning is better to use for the Python. So my student know about for the Python language well. So the other one, I'm interested for some events. For this is one of the events, Sakura Science Pro 2026. So just invited to my university from the university outside of Japan. And then, so this is just I'm sorry, this is 2025. And this time, so we some kind of the workshop for the coding of the first principle calculation, indeed based on the Python language. And then so here they got from the Gajah Mada University and the Bandung Institute of Technology. Also this time I invited from the Morocco University of the Moulay Ismail and also the Senegal University Gaston Berger University. So that's the introduction. So next one is I want to back to be my talk on the design of the interfacial material for the magnetic tunnel junction. This is a first principle studies. So first of all, introduction. And this time I want to show a method more detailed. I mean the basics, in basic side. And then after that, I give the two examples, perpendicular magnetic crystalline anisotropy and magnetic damping in the magnetic tunnel junction. Also, if I have a time, I want to talk on the spin hole conductivity in bulk and the whips. So it's a magnetic tunnel junctions. So this device is used in the MRAM, so the magnetic random access memory. And you can see here the left and right magnetization, and like this one, this is a 1 bit and 1 bit, 1 bit. And then this device is composed of the barrier layer of the mainly the MZO sandwiched by the metal, ferromagnetic metal for the pinning layer and the free layer. Okay, if the magnetization configuration is parallel, so its current flow on this way, but antiparallel doesn't flow. This is a simple principle to the switch on and off. So currently ratio of the tunnel magnetic ratio is, it's defined for the resistivity of the antiferromagnetic AP and antiparallel configuration minus the parallel configuration of the resistivity. And then in a device level on the MRAM, it's probably necessary to 100%. And in the lab, so there is a record for the 631%. It's very nice. And this is the history of the MRAM. So probably it's starting. So this phenomena is that found for it's based on the magnet resistivity. This one is found on the 1857. And after that, so this is a 1957 AMR, anisotropic MR, and giant MR. And then, so 1994, it's found for the tunnel magnetic TMR. And then this one is the first product, probably product is a STT-MRAM. This is in plane. So you can see the here magnetization direction is a parallel. And after that, you can see this one is a perpendicular one, look like this one, in plane to the outer plane to reduce or to get for the density, capacity, I mean the. And then now to be several MRAM. This is SOT MRAM. This is a very nice MRAM, and also the voltage assisted MRAM. So to look on these MTJ structures, so this is a very complicated for the structure. This is cited from the papers. So this is SiO, and this is electrode, ruthenium, platinum, cobalt, and platinum, cobalt multilayer, iridium, cobalt, platinum multilayer, tungsten, and cobalt boron, and tungsten. And here you can see the MTG junction. It's very difficult. Indeed, this MTJ or this material, so the multifunctional property are required. For example, pin layer, here you can see pin layer. So high perpendicular magnetic crystal perpendicular magnetic anisotropy, this one, perpendicular magnetic anisotropy, and also the high Gilbert magnetic damping constant. However, the in free layer, high PMA, but low damping constant. It's same the material, but it's necessary for the different kind of the property are required. Okay, this is some memory hierarchy in the electrode devices. And then so probably you know this is storage and the main memory, and this is cache and registers. It's the used for the DRAM and SRAM. However, there is some gap, speed gap between this one and this one. So to this, so probably MRAM, STT MRAM. This is a two-terminal devices. You can the current flow on this one, and we switching for the dismagnetization left to right or something. So next is the SOD. This is very high switching devices. So this one is three-terminal devices. On the writing current, you can flow from here to be this way. And in here, we use for the Hall effect, Hall current. So this is a spin Hall current. So we just compare, make a comparison for the memory devices. So MRAM is very nice, the property compared to the SRAM and DRAM. Also here is a flash, non-flash. And then so you can see the MRAM, first of all, the access speed is very good. It's comparable to the SRAM, and also the endurance is fine, and the power usage is fine, very good. And also the data retention is good, and writing speed is also very good. However, problem is the density. So compared to DRAM, yes, DRAM, this is high density, but the one order of magnitude is small. Therefore, the STT-MRAM, it still be necessary to include for the density. In case we need to be perpendicular magnetic anisotropy. Okay, next one is I try to show the calculation method. So this is some basic starting from the basic accept. So this is the electron structure. Everyone you know, we try to solve for this Schrödinger. This is a many body simulation, many body equations. So you can see this is the core. Core state is very localized on here. So you can see this is density of state. Therefore, this is localized. Therefore, we have a very sharp density of state with a small energy width. Compare this one, you can see here, this is the valence electrons. So in the valence electron, you can move for this way. And then so the bandwidth is increased, look like this one. And then so we can get for the Fermi level. And also we have a periodic potential, and we can get for the band structure. In case how do we describe for the wave function? So wave function, so we can separate it for core electron and valence electron. A core electron is look like atomic light. It's a change to boundary condition for the isolated system, but this one is a periodic system. In a periodic system, we introduce for the block functions. And then this is just theory of the electric structures. So we starting for the many body theory, and we use for the density functional theory, just described by the density for the total energy. And after that, we again introduce for the non-interacting one particle approximation. In this case, we can get for the very simple equation. This is a Kohji equation. So therefore, we try to solve for this equation by the computers. So this is a summarize for the Kohji equation. You can see this one is effective potential. So you can use for the exchange. This is the LDA or GGA, and this is Coulomb potential. And also this is a very difficult to work. The one particle wave function is a basis variable principle used for the variable principle. It's a basis. In my case, this basis used for the linearized augmented plane wave for this one. Interstitial we use for the plane wave, but the muffin thin sphere in the atom. This is the atom region that we use for the expansion of the spherical harmonics. So just the this is program DFT code. I make it is only the one page. You can make it for this one. Okay, very simple. And then I'm sorry, this one is a Fortran. I'm not familiar for you. This one, so we have a loop, very big loop, self-consistent loop. This is a K loop, and this is K loop, and look like this one. So detail is due to the time, so I want to skip for this one. So now go to the example, perpendicular magnetic anisotropy and magnetic damping. Okay, first of all, as I said, we want to get for the perpendicular magnetic anisotropy, PMA. I just say PMA, this one. So in case they how to design this film is a large PMA. Okay, this one is of course the coming from the spin orbit coupling. So spin orbit this way, and then so L and angular momentum operator and sigma is a spin operator, and this coefficient is spin orbit coupling. Usually this one is around the 50 milli eV for the 3D metals, not small. And then so magnetic anisotropy energy here is defined for the total energy difference between the magnetization oriented to the in-plane direction and out of plane. So in the case, negative number is show in-plane MA, and the positive number show the perpendicular MA, PMA. So here is some example for the monolayer. For the 3D metals, you can see this one. So the iron monolayer 001, cobalt 001, nickel 001. This is application GGA and LDA, and you can see the iron monolayer showed out of plane, but cobalt and nickel, it showed the in-plane directions. And then, so this is so we can discuss from the band structure. So now going to be MTJ junctions. Okay, this one is so ion interface between the ion MgO. First of all, we use for the freestanding ion monolayer without the substrate of the MgO. In a case, we have a positive number. This one is 0.2 milli eV unit area. So it shows the out of plane. And however, if you put the MgO subset, I mean the ion MgO interface, in case we have a 6-time increases. Okay, substrate, MgO substrate is enhanced for the PMA. This is simply explained by the ion Z squared to the PZ hybridizations. And also if you make a cap layer of the gold on this one, even in this one we have a 0.94. So still be out of plane, PMA. So more detail is I'll describe on these papers. So the experiment, this is a very famous paper. So my prediction is on the 2010, and this one is also the 2010. And then so there, this is MTJ junctions. So you can see this is cobalt iron boron and MgO and cobalt iron boron. If the cobalt iron boron, thickness of the cobalt iron boron is 2 nanometers. In a case out in plane, this is so the field, and this is a magnetization. And then you can see this one is the in plane direction, but the red one is out of plane direction. But if you're going to be a thin layer of the 1.3 nanometer in a case, so out of plane direction is look like this one, but the in plane case it look like this one. It shows the PMA when the thickness decreases. Okay, so the next is a problem. If the going to be high PMA, we have a problem in the small storage. So the if you're going to be a small one, I mean the we have to be keep on the thermal stability for the bit. So this one is parallel. This is anti-parallel. To get for the high thermal stability, we need to be energy gap. This energy gap. Okay, so energy gap. So the energy gap is described by the energy barrier height between the parallel and anti-parallel stated. However, we have to be switching by current for the direction of the direction on like this one, so up to down. In a case, we need to be current critical, the right critical current. In a case, this current is described by this one. Of course, the HEEF, this is PMA. So if we include this number, we need to be more the right current. So in a case, it's not good for the devices if we include for the current. Therefore, we have to reduce for this number. To reduce this number, we should be, so the damping constant should be low. So therefore, we have to be simultaneously realized for the high PMA and low damping constant. How do we design for this kind of the materials? So we first of all, we just summarize review for the experimental trend. This is the PMA, magnetic anisotropy, and this is a damping constant. Okay, our target in the device is this one. So the large PMA and lowest alpha damping constant, this one. However, material is going to be this way, high PMA, high alpha. Next one is also same trend. And furthermore, it's a Heusler alloy. This is a very good candidate, but there still be this way, slope is positive. But the target is this one. How do we realize for this one? So we try to be modified for the interface for the at here. This is a MgO, but we substitute for the X like the nitrogen and fluorine. So here, this is a result. First of all, this is a pristine structure. So this is a PMA about 0.6. Okay, alpha is about for the 1.5, like this one. If you substitute for the nitrogen and fluorine F, in a case we got for this one, especially for the nitrogen cases, it's a very interesting. First of all, PMA increased about 4 times. And also the damping constant is reduced for the 65%. It's very, very ideal, the interface or ideal the junctions. So now more calculation we have been done in a case. So the like this one, lithium F and magnesium nitride and the boron nitride is very good. So target is close to here. So the high PMA and low alpha simultaneously demonstrated. Also, they overcome the trade-off. So usually this way, but we got for this way, and target achieved or candidate for the interface modification. It might be good for the Mi-Jin N and BN lithium F, and very close to the target. So we have still be 10 minutes. And then, so I want to be going to be a next topic, spin hole conductivity in bulk and films. This is used for, this spin hole conductivity used in the SOT-MRAM. As I said, this is a three terminal devices. So this is a writing current this way, but the if current flow on this way, we got for the Hall effect. So this one is a spin Hall effect. So anyhow, the spin Hall effect, probably everyone, some of you know about for the phenomena, spin Hall conductivity. So this is if you apply electric field on the negative direction along to the x, so electron flow from the left to right. In a case, electron with the up spin is going to back. The electron with a spin down is go to the front. This is you can see the spin flow to this way to like this one or this way. Okay, so this one can be described for this one. So the EX and J, this is a spin current and this is a conductivities. So this conductivity, Y, sigma YX, can be obtained by the linear response theory. So this linear response theory, if you use the Kubo formula, very simple. So we just for the counting for this one. So this the bra and cat, you can see this one is a wave function for the Kohji equation, and we apply for this operator. This is a velocity operator. This is a current operator. If this Jy is a velocity, in a case we got for the anomalous Hall conductivity. If you change the spin Hall current, velocity of the spin, I'm not sure exactly. This is a spin Hall conductivity. If you change to this one to be angular momentum operator, in the case we got for the spin Hall conductivities. And then here to be, we also calculated for the spin Hall conductivity in monoatomic metal. This is a very famous for the Salam's paper on the physical review materials. We also using my code, we can demonstrate it for this trend. You can see this one, 3D system, okay? So the chromium and the manganese and iron this way, and here to be nickel is high. So we have this one is a negative number. This is a vertical axis show the, I'm sorry, this is a spin Hall conductivity. And then, so the nickel is a positive number. So negative to the positive, we got this trend. Going to be 4D system, we got for this is the niobium, molybdenum, and this one, it's a negative number. But if you're going to palladium, we have a positive number. Similar trend we have. And then we are going to be a 5D system. So this is a very good. The tungsten is a very negative, very big number. Currently, the SOT-MRAM people use for the tungsten. Okay, this is a beta tungsten. And then so the platinum, but platinum is a very high, still be this number compared to the tungsten. So the platinum is a very good material for induce for the spin Hall conductivity. But here we have a same trend and same trend and same trend between the 3D and 4D and 5D. And then comparison to experiment. So the tantalum, so this TA is here, and this the tungsten is increased. So we got for this one, and platinum, this is the absolute number, so 3.4. This is a very big numbers. So probably our calculation is also the catch for the experimental trend. So now we are going to be alloys. Alloys. Alloy is a very difficult because many combination of the atoms. atomic configurations. But we calculated many alloys, but you can see the trend is roughly same. So this one, the horizontal axis shows number of d electrons. Vertical axis shows the spin hole conductivity. So first part is this is rather negative. This is a positive number. But if you make for the alloy, unfortunately, we cannot get for the record number of the tungsten and platinum. So now going to be interface. This is a cobalt and 5D interfaces. So just the tandem tungsten, rhenium, osmium, iridium, platinum for this one. This is 16 layers. I'm sorry, this one is the number of, this is layers. And also the cobalt is one monolayers. Even in this case, the spin hole conductivity is same trend. So tungsten is, for example, 15 layer of the heavy metal. So the tungsten is a large number in negative, but the platinum is a more large number in positive value. So now I want to be extend to the device model. It's a thin films. So this one is electron flow on this one, and probably the up spin is go down and down spin is going up. So we can get for the spin hole conductivity, I model it for the 18 atomic layer of the platinum. Okay, this is a spin hole conductivity at one layer of the one layer of 2, 3, 4, 5, 6, like this 18 layers. So we have a positive number around to this way. So the hole conductivity is spin hole conductivity is flow on the bottom to right. Here is another proof for the hole spin hole current. So you can see this is a spin moment. So this is an electron field induced spin moment. So when you apply electric field, how much the spin moment induced. So when looking for this one, so we have a negative spin moment. This one is a positive spin moment. So this means you can see here at the end, we have accumulated for the spin up and accumulate spin down on this way. This one, so the spin moment at the surface are induced by applying the electric field. So almost I have a time, so I want to summarize, but this is just the content. I show the introduction of the magnetic tunnel junction, and I show the calculation method, and also the example, perpendicular magnetic crystal anisotropy and magnetic damping in the MTJ. Finally, we will still be working on this one, spin hole conductivity in bulk and film. Also, we now to be orbital hole conductivity is also the one of the very interesting phenomena. So thank you so much for the attention for a long time.
Thank you very much, Professor Nakamura, for the insightful presentation. Now we will open the question and answer session for 2 participants. Participant who would like to ask question may raise your hands, or for online participant, maybe can write in the Zoom chat. Okay? Yes. For the offline participant who ask a question. Okay.
My name is Hanif Kuduswada. I'm a third-year student from undergraduate physics student in UGM. Firstly, I want to thank you so much for the great explanation. It really takes my attention in these specific topics. But in my point of view, it still seems a little bit complicated. So I want to ask first is, for now, what is the current research trend for this specific topic for MTG? And also, what do you think for me, myself, as an undergraduate physics student, if I want to contribute in this topic? Thank you.
Okay, still we already with MTJ, we have a product. So go back to be this one. Indeed, I'm not for the developer of the MTJ and also not experiment. I am just theory and coding, making a code for the first principle calculation. Therefore, I am not exactly not sure for the current topics, but the colleagues say they need to be more high density of the bit density. In a case, this one correspond to this one, okay, more high. But in case if you include for the density, bit density, of course, we have to be need for the right current. So this is a rather big current. So the Joule heat is a problem. So therefore, we have to be reduced for the current, high perpendicular, but reduced for the current. This is one of the problem we have to be solved. Okay. The other question is, what is the second question? Study. In my opinion, so the study of the coding. No. But yeah, so now we have a nice code software for the first principle calculation. Probably you can use for this one, and then so you can extend to more nice code. And for the first principle, probably there is still be not perfect. Still be not perfect for the. Okay, this one is still not perfect for the predict for the every properties. So people working on still be some approximation to describe correctly. So like this one, beyond the LDA, this is one of the very interesting. Also the time dependent of the DFT is also interesting. Okay, probably so many things there is for even in this field.
Okay, thank you, Hanif, for the question, and Prof. Nakamura. Now, okay.
Thank you. My name is Zurnansha. Currently, I am a PhD student or doctoral student in the Department of Physics. It's something new for me actually for hearing the MTG calculation because currently I'm working with GMR. So there are several parameters that, according to me, same as to GMR. But there are many also parameters that's something new for me. I have several questions, and it's very basic, I think. My first question is, which or what the most critical parameters in MTG fabrications or in MTG calculations that very important and that would be able to maintain the stability of spin orientations, and at the end exactly to obtain the higher IMR ratio itself. And my second question is, instead of iron and MgO, as you mentioned in your presentations, which or what materials that has potentials that would be able to be applied for MTG calculations or fabrications? Thank you.
Thank you so much. Very difficult to answer this one. How do I say? I'm not I'm working with some collaborator who working on the MRAM, but they don't want to change for the system in experiments. But also now to be MgO, I'm not exactly don't know the MgO cobalt iron boron or cobalt iron has a very good property for realize for the MRAM. So next one, so in device model, they said 200% DMR is enough. Therefore, I hope this system is the best one. Of course, if you have another idea, candidate for the MTJ of the materials, you can propose. But I'm sorry, I don't know exactly for this one. What kind of parameter?
Yeah, I mean, what parameters, the most critical parameters
For the
in MTG calculations?
MTJ calculations.
Yes. Or MTG fabrications?
Application is so TMR is the most important parameter, I think. TMR. The other one is so next one is so going to be density or something. So it's better to be high PMA and low damping constant or something. So most one is a TMR. So you need to be a TMR value is a high number. I mean the 200 or 100. Exactly, I'm not sure the number, but I just heard from the colleagues so around 200. 100 is enough. You know.
Thank you for the interesting discussion and active participant. Now let us continue to the second presentation. Our second speaker is Dr. Mi-Jin JIN from the Institute for Basic Science, South Korea. Allow me to briefly introduce Dr. Mi-Jin JIN profile. Dr. Mi-Jin is currently a researcher at the Center for Multidimensional Carbon Materials, Institute of Basic Science, South Korea. Her research interests include quantum materials, oxide-based spintronic, and magnetic device. She obtained her combined master and doctoral degree from Ulsan National Institute of Science and Technology. As assistant professor at Kook University 2020, postdoctoral researcher, University of Cambridge 2018 to 2020, and postdoctoral researcher, Ulsan National Institute of Science and Technology 2017 to 2018. Today, she will deliver a presentation entitled Oxide-based spintronic. Okay, ladies and gentlemen, please welcome Dr. Mi-Jin JIN.
Nice to meet you. My name is Mi-Jin JIN. A little bit nervous. I will stand up here. Yeah. I'm from Korea and I'm working at Institute for Basic Science. And my institute, before talk about my research on oxide-based spintronics. I would like to introduce about my country, Korea, South Korea, and my country's companies and research institute, and especially my institute. Yeah, so as you know, South Korea is famous, recently really famous for several things like K-pop and K-dramas and so on. So our country is located similar with east side of Indonesia, and it has similar timeline. And actually, our country was combined with South Korea and North Korea, but it was separated at 1945. And nowadays, we only say our South Korea is shaped like this, and we have several beautiful places, including Jeju Island. So I am living in Jeju Island, so if you have a chance to visit Jeju Island, I hope you can enjoy our beautiful country's beautiful places, including Jeju Island. And we have several beautiful, some representative things I can say. We have, historically, we have famous great general Sun Sin Lee, and this is one of the famous King Sejong. He invented our country's own language, which is Hangul, several hundred years ago. So nowadays, because of the K-pop and K-drama, Hangul is famous for as well. And our country has, including several thousands of kimchi style and bibimbap, we have some famous food. And because of the K-pop Demon Hunters, our country's Seoul City is famous for as well. And K-drama is getting enlarged our country's, what should I say, representative things. And most of them is Squid Game. And BTS, you know, right? Yeah, it is really famous singer in Korea. So I never heard BTS's song, but most of my friends abroad, I know about them. So maybe I hope you guys enjoy Korea. And we have not only for K-drama and K-pop, we have famous company as well, Samsung, LG, Hyundai, and Kia, and SK Hynix as well. Nowadays, SK Hynix is really increasing company related with the semiconductor as well. And we have several national institutes, including KIST, which is the multidisciplinary field. And the other one actually is related with AI and aerospace, atomic energy, mechanical thing, and geoscience as well. And we have some combined university with research institutes such as KAIST, GIST, UNIST, DIGIST. So among them, my Institute for Basic Science is especially, which is established at 2011, and it is especially focused on basic science, natural science. It's like physical science and earth science, mathematical, and chemistry, and so on. So our institute is accelerated transportation through new knowledge and excellence in research. And to tell the truth, our institute is scored for Nobel Prize, and it's inspired and motivated from Max Planck Institute. So we have seven research institutes and 31 research centers all over the country, on our country. So as you can see here, several research institutes and centers we have. And as you can see here, we are all around the country. We have 5 institutes in Seoul City and Suwon, Daejeon. We have head office here. In GIST, in Gwangju and Busan, and Pohang Postec as well. So this is Ulsan City, and I am working at this UNIST, Ulsan National Institute Campus Center. And my institute head office, director is Professor Roderick. He's really famous for graphene and carbon oxide related materials. And we have 4 representative professors as well, which is co-professor with UNIST University. And I am working as a young scientist fellow, and I'm just a small team leader. And from next September, I will move to POSTECH. So here, yeah, do you know POSTECH? POSTECH is one of the famous institute at Korea. So I will move to here. And here we are focusing on some van der Waals quantum solids and geometry and physics and artificial low-dimensional electronic system. So here is my next position building, and my next director is Professor Munojo. And with Munojo, there are several professionals are working there, and they already published several representative papers. And a special thing at my next institute is the equipment, amazing equipment system. They have in-situ equipment system which can grow van der Waals material or TMD material, and then directly they don't have to take out the sample. Directly they can deposit another metallic or oxide-based material, and then they can measure or spectroscopic characterization by such as STM, AFM, and so on. So they can do deposit molecular van der Waals heterostructure here, and they have a specialized variable spectroscopy. So if you're interested with Korea and Korea's research institute or university, please join us. And if you have any questions, you can contact me. Yeah. So now I will move on to my research on oxide-based spintronics. So my subtitle is Spin and Charge Transport Study at Functional Oxide System. So actually I prepared this brief introduction about spintronics. As you know, the electronics is using only electrons, but spintronics is using not only electron, but also electron spin itself as well. And there is 2 types of mechanism of spin orbit coupling, which the first one is intrinsic spin orbit coupling. This one is related with the structural inversion symmetry breaking at a solid, and the extrinsic spin orbit coupling is related with impurity or vacancy and so on. So from this spin orbit coupling mechanism, I am using 2 types of effect. The first one is Lashba-Edelstein effect. This is related with the interfacial effect, interfacial spin orbit coupling mechanism. So, but this one, the previous professor didn't explain about that. I will briefly show that. This one is based on, originated from Lashba type spin orbit coupling, which is related with the interfacial effect. So if there is Lashba type spin splitting exists and there is a current flow is going through, then there is current induced spin accumulation. Up spin will flow through this more quantity at here, and down spin has more quantity at here. So accumulation can be happen at the moment. That is the spin charge to spin conversion, which is the Lashba-Edelstein effect. And if you want to detect this Lashba-Edelstein effect, you need to use inverse Lashba-Edelstein effect. This is the spin to charge conversion. So if there is current induced spin accumulation is happen, and then if you do make some kind of high spin orbit coupling material at the interface, then you can detect the spin induced charge accumulation. This is the inverse Lashba-Edelstein effect. And the other one, what I usually using is the spinol effect. This one is already previous professor explained. This spinol effect can be happen not only bulk but also interface as well. So I'm using usually I'm using these 2 types of spin orbit coupling related effect. So this is my research, 3 major research related with oxide, full oxide structures. So the first one is the spin manipulation and oxide-based system. This one is I'm using spin Hall effect. And the other two is the functional charge transport. This is also related to spin, Lashba spin splitting. And the third one is a spin to charge conversion or spin orbital at magnetic oxide full structures. So this one is using spin Hall effect. The other two is Lashba type spin Lashba-Edelstein effect, which is the interfacial spin orbicoupling effect. So the first one I'm using is LaO-STO epitaxial structures. As you know, the lanthanum aluminum oxide, then strontium titanium oxide has large band gap, which is relatively, we can call insulators. So, but these two insulator has epitaxial relation, then at the interface, there could be two-dimensional electron gas. The conductive interface can be happen. This two-dimensional electron gas has interesting physical phenomena due to coupling between charge and orbital and spin. And it has also great possibility for device applications because it has mobility up to 10,000. So this is one of the interesting playground of oxide-based material for spintronics. So after experimentally 2004, Harold Hwang group reported the LaO-STO 2DEG. After then, there is several hundred of papers are reported, including superconductivity, ferromagnetism, and coexistence of superconductivity and ferromagnetism. Among them, the first spintronic study by using this LaO-STO system is the spin injection method. At 2012, they used spin three-terminal geometry and they used the cobalt material. And if they apply current through this electrode, then the spin polarized current will tunneling through this interface. And then with applying external magnetic field, you can obtain the spin precession signal, which is the Hanel curve. But this is three-terminal geometry-based spin injection method has some negative point. The one is a signal do not rely on real spin transport, and the other one is controversy on Hanel signal in three-terminal geometry. So one of the other idea was using the spin Hall effect twice at the interface. So the idea is shown like this. If you do make this kind of whole bar H-bar type geometry devices, and then if you minimize the ohm effect, and if you do control these geometry factors, then you can apply current from here to here. And then because of the spin Hall effect at this cross, the spin polarized current will flow through this channel. And then one more time, because of the inverse spin Hall effect at the next cross, you can obtain non-local voltage signal at this line. So this is the spin Hall effect induced spin detection without ferromagnetic material. So at the first time, experimentally at 2D material at 2013, they used graphene material, and then they do measure this at these geometry devices, and then they do measure this spin precession signal. With the same idea, I designed this H-bar type geometry devices, and then I will apply current from here to here through the interface, and then I can measure the spin Hall induced no-local spin signal. So to make this geometry device, I need to set up fully oxide-based fabrication process. This is relatively different from silicon-based semiconductor devices. So I did develop this one. So I used 2 times of plasma treatment and patterning processes. I successfully obtained the patterned devices, as you can see in this figure. As you can see here, I used 4 channel at 1 sample, and then to choose this channel width and length ratio and width value, I need to consider this spin origin. So I need to minimize the ohmic effect, and I need to efficiently detect the spin hole-related current voltage detection, I used this one. So you can see, if, for example, channel width case, in diffusible limit, channel width is much longer than electron beam prepass, and ballistic limit, channel width is much shorter than electron beam prepass. So if you do want to measure the spin hole effect related signal, and if you do want to minimize the ohmic signal, you need to make channel width needs to be between electron beam prepass and spin diffusion length. So after obtaining that spin hole region, we choose channel width around 500 nanometer to 1 micrometer, and channel width and length ratio needs to be more than 3 times. This is the key. And then after this basic property checking, such as linear relationship of this IV curve and temperature dependence resistance of the interface needs to be metallic behavior, and mobility and carrier concentration depends on temperature were measured. And then for this is the main data you can see here. Again, if you apply current from here to here through this interface, LA or STO interface, then because of the spin hole effect, you can imagine that spin polarized current will flow through this channel. And then with applying external magnetic field, you can obtain the non-local voltage signal because of, one more time, inverse spin hole effect at this cross. So this is the spin processing signal. So at 0 point, there should be maximum non-local resistance. And then if you apply external magnetic field more, then because of the spin precession, the resistance will be decreased like this shape. This is the Hanil curve. So depends on channel length from 2 to 5 micrometers, the maximum non-local resistance shows like this behavior. And you can directly fit this behavior using this equation. Then you can extract the spin diffusion length is around this value and spin hole angle is around this value. And also you can directly fit this spin precession signal using this equation. Then you can obtain the spin hole angle around this value, spin diffusion length as well, which has agreement with this value. And then for more detailed analysis, we did spin precession signal from 2 Kelvin to 20 Kelvin. Then you can see the precession signal is decreased and then it's disappear at 20 Kelvin. So after calculating from this equation, you can extract this spin lifetime, hole angle, and spin diffusion length, and maximum non-local resistance can be decreased with increasing the temperature. This is the reasonable value as well. And then also from the mobility calculation and carrier concentration calculation and so on, you can think about the majority relaxation mechanism dependence at the interface. So with this relation of Elliott-Yapet mechanism has some momentum scattering time. It has this relationship, and this diagonal parallel mechanism has inverse relationship. I mean, negative relationship with momentum scattering time. And then you can see at this LSTO 2DG interface has majority dependence of diagonal parallel mechanism. This is the structural inversion symmetry breaking related mechanism. So those analysis can show the reasonable behavior as well. And from this study, I would like to say this is the first demonstration of spin injection and diffusion without ferromagnetic material. And with similar with this study, I did studied about pure STO2D surface as well. STO surface is normally it shows insulating behavior, but if you do treat making some kind of defect and vacancy by using plasma treatment and so on, you can make some higher conductivity surfaces. Then and then you can cap with the MgO material and so on. Then you can measure this kind of spin precession signal as well at your surface only too. So at this study, we also proved that pure spin current is reacted for spin processor signal or not. So if you do measure the external magnetic field with the three different directions and 9 components of in detail external magnetic field direction, you can see the spin precession signal is only showing at BY direction. So which means that the pure spin current, only one direction of electron spin is reacted with for the spin precession signal. So about the mechanism we discussed about on the papers, and we also calculate that characterization value of the spin diffusion length and spin lifetime and so on. From this study, so we did make the surface defect dominant system, which is spin Hall effect enhanced system. And then we did measure some, we did show some another proving method to see the pure spin current is reacted with it. Yeah, from until now, I showed the spin Hall effect induced spin current detection without ferromagnetic material. And for this one, I would like to show you some functional charge transport at oxide-based interface. This is also used for by using LA or STO system. But at this experiment, we did focus on the 2D, which is the Lashiba type spin orbit coupling detection at this interface. So you can see here, one of the methods to detect the Lashiba type spin orbit coupling is to measure planar anisotropic magnetic resistance. As you can see in this page, and when the Lashiba type spin orbit coupling is not big enough, then conventional planar Hall magnetic resistance shows the same resistance value at opposite direction of external magnetic field, as you can see here. But if the Lashiba type spin orbit coupling exists and it is big enough to detect, then you can measure the clear resistance difference at zero direction of external magnetic field and 180-degree external magnetic field. So with calculation about this, at our sample system, we also obtain these clear resistance differences, and then we start to make some in detailed plan. So you can see here, here we start to, we try to measure, experiment, systematic measurement to see the Lashiba type spin orbit coupling spin splitting exists, and we can measure some other, which is the non-reciprocal charge transport of this LAO-STO system. So we make this simple whole bar geometry devices, and then if you apply current from here to here, or if you apply current from here to here, and with applying external magnetic field with this direction, then you can imagine there is Lashiba spin splitting, and the other direction of spin splitting can be happen because of the external magnetic field. So after this two types of spin, because of these two types of spin splitting, you can obtain the clear resistance differences at this plus current and minus current, as you can see here, this graph. And if you apply backgate voltage from minus 10 volt to 80 volt, then you can see the resistance differences are showing like this behavior, depends on backgate voltage. And the resistance difference shows maximum value at below 10 Kelvin, which in our experiment, it shows 8 Kelvin temperatures. And for systematic analysis, we did measure AC electric field dependent, angular dependence of non-reciprocal charge transport. And we measure 2 omega resistance using lock-in amplifier. Then you can see there is clear resistance change depends on external magnetic field, and with 3 different external magnetic field direction. And if there is no Y component, then the 2 omega resistance shows minimum value. And if there is Y component, then it shows clear resistance change, depends on angle change. So you can see here, depends on backgate voltage and current and external magnetic field. You can see 2 omega resistance shows this behavior depends on backgate voltage which has agreement with this value, and depends on current. You can see the linear relationship, and external magnetic field has some higher orders of dependence as well. So from this study, we showed that oxide material system, we first discovered the non-reciprocal charge transport. So from this report, we have one more papers. And this one, from this third one, I start to add ferromagnetic oxide material. So this one is using ferromagnetic material. But this third one is not only using 2D interface, conducting interface of the oxide material, but also we use the ferromagnetic oxide material. So as you can see here, if you use the ferromagnetic material, then you can do study about spin injection and detection method, or you can do study about spin torque, ferromagnetic resonance study with the spin pumping method. So as you can see here, if you do apply microwave signal at the ferromagnetic material, and then the ferromagnetic resonance will be happen at the FM layer, and then the spin will flow through this interface, and you can measure the spin pumping signal. For this study, I developed this cryogenic FMR system. You can see here, sample will be put here, and the Helmholtz coil will be modulate the external magnetic field. And then you can measure the FMR signal using lock-in amplifier with the derivative Lorentzian function. And if you do connect the interfacial layer, then you can obtain the spin to charge conversion, which is the spin pumping signal by using nanovoltmeter. So I designed the ferromagnetic oxide material, and then I made the Kohji 2D interface at this interface. And then if you do measure this voltage signal at this, then this is the spin to charge conversion detection. And this is the evidence of the spin orbit coupling at the interface. So similar with the previous fabrication process, we can just deposit magnetic oxide at this, in between this process. And then you can see, if you do make this LCM, I first choose this LCMO as a ferromagnetic material, and then you can see LCMO and Kohji 2D has here. And for the structural analysis, the LCMO has the epitaxial relation with a similar XRD diffraction of STO, and the LCMO thickness was analyzed by using X-ray reflectivity measurement. It shows around 15 nanometers, and it has magnetic behavior with decreasing temperature, as you can see in this figure. And it has TC around this value. And for the 2D interface, we measure this temperature-dependent resistance, which shows metallic behavior, and it shows mobility around 10,000 at low temperature region. And this interface is relatively, we can easily distinguish with the LCMO material. So LCMO material has semiconductor to insulator behavior with decreasing the temperatures. So at the first time, we measure the LCMO ferromagnetic layers magnetic property by using ferromagnetic resonance. You can see here, from microwave signal from 5 to 15 gigahertz, you can see the resonance signal is clearly coming. And then you can extract the resonance field dependence frequency by using this equation. And frequency dependence delta H, which is full width half maximum value, by using this equation as well. And then the characteristic value of gyromagnetic ratio and effective magnetization and Gilbert damping constant and so on can be extracted by using this one for this equation and this one for this equation. Then you can obtain the Gilbert magnetic damping constant of this LCMO is showing like this value of my sample. And then at the same time of the ferromagnetic resonance detection, you can measure the spin to charge conversion voltage detection, as you can see in this figure. So at 2 Kelvin, 10 Kelvin, and 5 Kelvin, you can obtain the spin to charge conversion detection as well. You can see here, the conversion voltage signal is decreased with increasing the temperature. And after this obtained observation, you can extract the effective spin mixing conductance by using this equation, and then spin diffusion, spin density by using the equation. And then you can extract the spin to charge conversion, which is the inverse Lashba-Edelstein effect efficiency around the 2.32 nanometers, which is, this is because the two-dimensional characteristic value. So this is the same component with the spin diffusion length. This is the evidence of interfacial spin-orbit coupling. So from this study, we would like to say we show strong spin-to-charge conversion via interfacial spin-orbit coupling at Kohji 2D LCMO and conducting STO interface. And this is the last one. How much time do I have? 5 minutes? Okay, I will quickly do. From this same material, we can also study about the spin orbital. The previous one was a spin to charge conversion at the interface by using ferromagnetic material. But at this time, if you apply current through this high spin orbit coupling, interfacial spin orbit coupling material system, then the spin orbit torque will be effective to the ferromagnetic material. This is the inversion case. So we study about this one as well. So this is the same sample, so I will just skip it. As a result, you can see here, if you apply current through this interface, and then with applying external magnetic field, you can see clear planar hole resistance change and magnetization switching is shown. And with opposite current direction, you can see there is clear clockwise to anti-clockwise magnetization switching is shown. And for more clear provement, we did apply pulse current, and then we measured the hole resistance as well. So at minus field to plus field, the magnetization switching is clearly shown. And furthermore, you can see the anti-clockwise to clockwise change is clearly shown, depends on external magnetic field. And at zero field as well, you can see the magnetization switching behavior is coming. So with the systematic analysis, we did apply external magnetic field with different quantity, and you can see it shows some this hysteresis-like behavior. And over the 50 millitesla and minus 50 millitesla, it shows only one direction of magnetization switching direction. But in between minus 50 to plus 50, it shows some plus to minus, minus to plus, clockwise to anti-clockwise. It shows the randomly. But this is the similar component of the coercivity of the LCM material. So it is a clear provement as well. And from this study, we summarized this kind of study of the spin orbital induced magnetization switching, and it is also field-free magnetization switching. So nowadays, it is not under review at materials today. So this is all about the oxide-based spintronics, what I'm doing. And for not only oxide-based spintronics, I'm doing some other study as well, such as charge transport, specific quantum mechanical charge transport study at TMD material. And also I'm doing some kind of collaboration research, such as defect engineering at oxide material system. This is collaboration with Professor at Jeju University. And as a ferromagnetic resonance related collaboration as well, I'm doing such kind of great research as well. So this is my collaboration. And recently I am planning to hire postdoc researcher and student researcher as a PhD course as well. So if you're interested in, please contact me. Yeah, that's all. Yeah, thank you so much.
Thank you very much, Dr. Mi-Jin, for the insightful presentation. Ladies and gentlemen, we will now open the second question and answer session. We will take 2 questions from the participant, and we have an exciting door prize for 2 offline participants who asked the question.
Okay, thank you, Doctor, for the nice presentation. So my name is Finan, and first, I'm not too familiar with experiment like transport measurement because I'm working with computational. So I'm just want to make sure first that at the interface you say that we have STO and LAO, and the spin hole conductivity is happening at the interface of the materials. Is it correct?
Yeah.
Or yeah. So yeah, I'm just curious about how to measure the conductivity when we have like an interface, how to make sure that it happens at the interface of the materials, for example, like using the whole bar.
Yeah, that is actually a great question. Experimentally, contact the interface is really hard. So at the first time when I did start to do oxide-based spintronics, it is really hard. If you just deposit electrode by using metal at the end of the geometry device electrical line, it is not working, because if you do decrease the temperature, then the contact will be separated with the interface and electrode material. So you need to make as much as possible area of the contact line. So you can make, for the tip, you can make not only just a square shape contact, it will be not working. So you can make some dot pattern as well in the center of the square shape, and then you do make that kind of design some contact shape, then you can obtain the stable resistance all around the temperature from 2 Kelvin to 300 Kelvin, like that. Yeah, it is really hard. It's technique. Yeah, engineering technique. Yeah.
Thank you, Doctor.
Thank you for the question. Okay, we still have one door prize for the participant who asked a question.
How about BTS? K-drama? Oh, right. Yeah.
Yeah, in the term of spintronic, MTG, and MRAM and everything, I'm not so familiar with the oxide-based materials. Maybe you can explain what is the special thing, or the the beneficial if you use the oxide system in the MTG, something like that.
Yeah, that is good question as well. Most of the device application is focused on metallic-based system, but oxide-based spintronics and its possibility for application has a little bit far from realization, but it has a positive point for temperature stability. Even though low temperature to high temperature, oxide material is not degradation performance, because it's already oxidated, so it is really stable for that. And also, if you do control some interface well, then it can make superconductivity as well. For example, strontium titanium oxide, it has a superconductivity at low temperature. So it has some wide range application as well. So it is good. Yeah. But it's for the real application, it has some, we still have to do so much things. Yes. Yeah.
Thank you, Dr. Mi-Jin, for the answer. Thank you for the interesting discussion. Let us speak a big round of applause to our two speakers, Professor Dr. Kohji Nakamura and Dr. Mi-Jin JIN. Ladies and gentlemen, we will now proceed to the appreciation session. May I kindly invite to our invited speaker, Professor Dr. Kohji Nakamura and Dr. Mi-Jin, to come forward to accept the souvenir. And may I kindly invite Dr. Herlan to present the souvenir to our speakers. Thank you. Next is the photo session. Could the committee please help arrange the seat in the front of this room? Yeah. To all participants, please come to the front of this room. And for all female participants, please stay in the lower stage. And to all male participants, please come to the stage.
Mas, satu. Yang ini ada rollingnya. Rollingnya ya.
Untuk peserta perempuan, tolong tetap di bawah ya. Nanti kita fotonya di bawah. Terus nanti yang laki-laki bisa naik ke atas panggung. Yang laki-laki silahkan naik ke atas panggung, yang perempuan di bawah ya. Iya.
Maybe you get, yeah.
Ya, yang masa daftar tuh. Masa daftar.
Ayo, teman-teman.
Dikasih.
Sini ya. Iya, Mbak. Aman, Mbak. Sini. Umpetin.
So everyone who want to sit in here, so please join the PSD, okay?